Mahesh, in the morning, he talked about how the third edition of this fantastic session or this event is going to be where there will be a lot of professional participation between the various companies and the IITM alumni professors. So what Murli and I have done is, in the last few days, been working with the professors, taking them to various industries, various companies, Tesla being one, ZenLab, here to see today, and applied materials. So we've had fantastic meetings where we looked at various high-value problems, how it's relevant to what work the IITM professors are doing, so that we could think of the next step and how we can actually collaborate. So that's one thing that I want to let you know. The second one is recently there was a Dare to actually a Dare to Dream contest from DRDO. And this was actually an innovation contest in India, and I'm happy to know that out of 600 applicants, there were 12 finalists, and the top spot was actually backed by Dr. Rao here, his team. So please give him a round of applause. So that shows how that it's not just an academic institution, it's actually working with startups, working on solving problems. And this particular problem that we were actually solving was using diamond coatings and materials engineering using diamonds to actually use for a space application, especially during the re-entry of the space vehicle, and how that diamond can be used to actually thermally be very conductive and also reduce the payload. So this is actually very relevant, especially with the moon mission recently from India as well. So that's something that has been done incredibly well out of IIT Madras using materials research. So that's very relevant to what we're going to talk in today's panel.
Thanks, Bharat. So normally materials is kind of an ignored section in the Bay Area, right? In Valley, usually it's about software, it's about other things. But I think now, with all these new materials, it's not your, as I said, it's not your dad's material science anymore. It's new nanomaterials, and there's a big revolution going on in material science, especially the theme of this summit being energy, environment, and sustainability. So we have a good panel of speakers, and let me introduce our session moderator, Harish Kamath. Harish is Program Manager for Energy Storage at EPRI, which is Electric Power Research Institute. He manages the Institute's research into development, assessment, application of energy storage technologies for grid storage applications. He's also a technology scout for the EPRI's Technology Innovation Program, where he investigates advanced materials technologies for power delivery applications and advanced energy storage technologies. So that's one of the reasons we approached him, and he was kind enough to agree to moderate the session today. He has a bachelor's and master's degree in chemical engineering from Stanford, and before that, before EPRI, he was at Lockheed. He was applications engineering and business development manager at a startup energy storage company after that. So welcome, Harish, and thanks again for hosting this session.
Thank you very much. Thank you for the kind introduction. And thank you for the invitation from the Alumni Association. It's a great pleasure and an honor to be here and to also introduce this wonderful panel of distinguished speakers today. Just briefly to tell you where I'm coming from on a lot of these things. As many of you know, material science is foundational to so many of the technologies that we do today. Many of the advances that we've seen, even over the last 20 years in IT, wouldn't have been possible without the continual advances in material science that go into that, in the semiconductor area, in the photonics area, in so many different other areas of technology. And so, although many of these technologies are not immediately visible, they're extremely critical to the continued advance of technology. And so what you'll be hearing about today is some of the very interesting things that are happening, not only in the academic area and particularly in IITM, but also in industry. So we have two speakers from IIT Madras, who will be talking about the academic research, and we also have two speakers from industry who will be talking about how those are being applied. So I just really want to briefly talk about where I'm coming from, who I am. As Louis said, my background is in energy storage, but I also do material research, and there's a lot of material research in the electric power area around things, for example, as cable insulation or coatings for transmission lines. So one of the things that we do at EPRI, Electric Power Research Institute, is to ensure the safe, reliable, affordable, and environmentally responsible production and use of electricity. So we're a nonprofit organization that does public interest research in the space, funded largely from the electric utility industry, but also from government agencies and from industry partners. So our role in this is really as a technology accelerator. We take basic technology coming from the national labs and the universities, as represented by ITM today, and get them through that initial phase of vetting, of enhancement, of commercialization into the actual commercialization area, which is some of the work that you'll be hearing from Dr. Walker and Dr. Kumar today from the industry side. So we try to enhance that, especially in the electric power area, because it's a very conservative area. Right? Electric power, everybody is worried about two things: reliability and cost. And so innovation is not important in electric power today, but it is important. And so we have to make sure that we actually catalyze that development. And this is all going towards a future of electricity today, which is focused increasingly on the customer rather than on low-cost supply or on just delivering the lowest cost of energy. People are very interested in where their energy is coming from. And so the question today, that the three big trends in electricity are decarbonization, going towards a zero carbon grid, decentralization, meaning that we're able to generate energy anywhere across the chain, including at the end use point, through distributed energy resources, and digitization, increased involvement of information technology and IoT devices all the way through the grid to enhance operation and efficiency of the grid. So all of these things require advances in material science, and that's really where we're looking at it. So I'm going to introduce my panelists, who I'm going to invite to come up and join me here on the at the front. Actually, you guys want to watch the presentations, right? So I'll let you sit in the audience as you give the presentations. I'll introduce the four people. So we're going to first hear from Dr. Sujit Kumar, who is the CEO of Zen Labs, a high-energy, high-power battery startup here. Dr. Kumar, and then we'll hear from Dr. Rao, who's in the Department of Physics at IIT Madras. You saw his presentation earlier today on the solar harnessing department there. Then we'll hear from Dr. Walker, who's the CEO of Ravio, who's doing some interesting work with solid-state lighting and using solid-state lighting devices to purify water. And then finally, Dr. K.G. Pradeep, who's also at IIT Madras, will be talking about combinatorial alloys and magnetic materials. So let me first introduce Dr. Sujit Kumar, who will be talking about his work in advanced battery technology. Dr. Kumar is a graduate from BTech from, come on in. BTech from IIT BHU in Varanasi, and also a PhD, he received his PhD from the University of Rochester for having quite a storied career actually in several battery startups and other companies in this area, having been funded by DOE and several different agencies, Office of Science, RPE, and deeply involved in the U.S. Automotive Battery Consortium, if you're familiar with that, very important agency. So, Dr. Kumar?
Thanks, Harish, for the introduction. Choose some.
Oh, yes, I'm
Just go here. So I co-founded Zen Labs with a mission to provide high energy density, fast charge, and low-cost battery solutions that will enable the mass adoption of electric vehicles. Brief overview of my company. We are located in Fremont, California, and we have a commercial cell prototyping center in Jiaxing, China. So that's why we are looking at a couple of pictures. The long battery is about 60 amp hour battery that's being used in Chevy Bolt, and on the right is a 27 amp hour battery that's used in Chevy Volt. So we work very closely with GM, Ford, Chrysler, and you use about a few hundred of these cells in a car. Our core technology is a silicon-based anode. You will hear a lot from Professor Pradeep as well. I had a pleasure to host Professor Pradeep, Professor Rao, and IIT Madras team at my company yesterday. Very fruitful, very intellectual exchange. So we are trying to replace graphite with silicon. Graphite has dominated for last 25 years. Every lithium-ion battery used has graphite-based anode. So that's what my company is focused on, how to replace graphite with silicon, which will have at least 5 times more capacity and double the energy density. We are very fortunate to work with tier 1 OEMs like GM and Ford, Chrysler in the US, and we also work with 2 European OEMs, and which is very important for a startup to make sure that you develop a product that can be commercialized. And we are almost reaching no commercialization timeline on this. And then another is we are in China. We have set up some manufacturing partnership. That's something I want to point out. Like, unlike Tesla, we can't raise $1 billion to set up a fab. So there are 2 models. Either you raise billions of dollars to set up your gigafactory, or you set up partnerships. So we have set up some manufacturing partnerships in China. The lithium battery is reaching theoretical limits. So the Moore's law for batteries is 25 years. It takes 25 years to double the energy density. If you look at your smartphone battery today, whether Apple or Samsung, Sony introduced it in 1991 with lithium cobalt oxide as positive, graphite as negative. Even today, these trillion-dollar companies, they have not moved the needle. All your smartphone batteries are based on graphite. So it's a very hard problem, and over the 25 years, all the improvement has happened by reducing the inactive material from the battery. Keep packing more active materials like graphite or lithium metal oxides, but no fundamental change has really happened. So in our case, we are developing 400 watt operational battery using a silicon-based anode. Also, I show you this curve on the right. There's a massive growth projected in EV batteries. Today, we have about 100 gigawatt hour of EV battery manufacturing all over the world. But next 10 years, at least 1.2 terawatt hour of factory capacity will be installed. At least half of that will be in China. So we have to put India on the map. Right now, there is zero manufacturing in India. All the smartphones, everything, all the batteries come from China. So that's why I felt this is a very good exchange that, why the labor cost in India is cheaper than China, but we do not manufacture these batteries in India. We do have, strong base for lead acid battery in India, but not lithium-ion batteries. And I'm a strong believer that public-private partnership, public-private, educational institutions like IITs, we have to play a role to put India on the map. I'm not to spend much time on this. This is the problem we are solving. There's a region people use graphite today, not silicon, because when you charge a silicon-based battery, it can expand by 300%, and when you do multiple times, silicon will fracture and it cannot be used. But the point I'm making is, as a small startup, we have to solve fundamental science problem. We can't do it alone. That's why this exchange is very important. As a startup, we can't afford to buy a scanning Interlink electron microscope, which I know is readily available at IIT Madras. We can't do neutron diffraction. Now, what's happening to silicon structure? But the PhD is working for Professor Pradeep and Professor Rao. They can solve those problems. So these are the things I want to highlight why there needs to be cooperation between educational institutions, startups and others, because this is not software, this is fundamental science. You need to overcome them, you need to understand them. If you don't understand today, this will bite you back 2 years from now. And automotive is a very conservative industry, so you just cannot put something in your electric car that you don't understand. Finally, how we are enabling mass adoption of electric vehicles. We are developing a very high energy battery. So today, industry standard like Chevy Bolt is about 240 watt-hour per kilogram. We already developed 350 watt-hour per kilogram, pushing it to 400. This will enable long range. Very fortunate that we received an award of 7.7 million from USABC, which is a consortium of GM Ford Chrysler. We used that money to develop high energy battery. Most recently, a few months ago, we got 4.8 million award to develop a fast charge battery. So we're already showing data that in 15 minutes we can charge 90% and we can do at least 600 times without battery degradation. So now think of it that this technology will enable 300-mile car. You can charge 270 miles in 15 minutes. Now you are having a parity with gas stations, right? That's very important for mass adoption. And then last but not least, the cost is very important. Fortunately, lithium-ion battery costs have reduced. They used to be $1,000 per kilowatt hour, now $100 to $120 per kilowatt hour. We are pushing the cost down to $75 per kilowatt hour, which means profitable electric cars. That's very important because today GM Ford, they sell cars but they're not profitable because of the battery cost. So with that thought in mind, I will conclude and let the next speaker.
Thank you very much. Yes, sir. Sorry? Hey, I think we'll wait a few moments. Actually, if you want to see the other presentation.
Yes, I would like to see this.
That's the great thing about it. So our next speaker will be Dr. M.S. Rao. Professor Rao is, of course, you already heard from him this morning at IIT, and is working on nanomaterials and thin films. His background, he is an MS and PhD from IIT Kharagpur, right? And has done his fellowships in France, Germany, Japan, and the US, all over the world, and has over 100 published papers and 6 US patents. So,
thank you. So I'm back again. So what I'm going to talk today is mostly about our research, basic research, applied research, how we work closely with industry, and I'm also going to tell people who are, we had a very fruitful discussions with the Applied Materials Group the whole of yesterday afternoon. Many common areas of interest, because the commonality is metal oxides. Okay. Now, this the roadmap that we did in 2016, a very popular one, about 200 citations in 2 years, and what Murli said in his speech, about materials, the interest and all that. Actually, in Bay Area, there are lots of, especially the universities here, the UCB, UCSB, there are lots of very strong materials groups. In fact, when I invited those people to contribute, they all did, and because of the importance of what's happening in oxide materials. Now, Intel is also, their future devices are going to be silicon plus oxide-based devices. They'll come out of this mindset that it's only silicon, but then they have to adopt oxide-based devices, so that integration is going to happen in the next 10 years. So that's where 2B stands for towards oxide-based electronics. And just one of the papers that I picked from 25 articles that appeared in that roadmap was a simple material like zinc oxide that we work on. We make nanostructures, we look at the light emission properties. Industries that want to invest should surely pursue this, because zinc oxide is going to be a very important, crucial material if you're thinking of replacing gallium nitride-based LEDs. It has the potential to replace gallium nitride. If we look at this, the chart here, the forecast of zinc oxide-based electronics market for LEDs, displays, UV detectors. The UV detection, of course, we have gas, gallium arsenide gas layers, but then the range at which the detection happens is in the deep UV, but from 280 to 400 nanometers, if you need UV detectors, it's based on zinc oxide. Then sensors, gas sensors and biosensors. So what is important about oxides is, if you look at this left side chart, you have a great choice of materials. And then you can process materials at very low temperatures to realize different kinds of mobilities. And this doesn't happen with the normal silicon-based electronics. And in terms of tuning mobilities, if you look at organic materials and asilicon, LTPS, you need to choose different types of materials in order to get tunability in mobilities. But oxide materials, you see that they cover a wide range, almost from 1 to 100 centimeters square per volt second. And when it comes to functional materials, there's nothing better than a technique called pulse laser deposition, which we use in our lab. We have established even home-built chambers for large area PZT growth. We were discussing about it yesterday. Ferroelectrics, high temperature superconductors, magnetic field sensors. For all these materials, the answer is pulse laser deposition. Today, if you look at this, it's amazing. All this is done in our lab. We could do these large area coatings for defense applications, flexible ones, and of late, recently we even demonstrated that high quality graphene could be grown with PLD. So looking at electronic applications, because CVD grown graphene is good, but it has surface defects, but the PLD grown graphene is really good. So all these things can be done. We can tune the parameters and get extremely smooth surfaces for tunnel junction applications and self-organized nanostructures. We have even demonstrated light emission from one-dimensional zinc oxide nanorods. I'll quickly skip this part because morning I explained this, the 4 pillars of solar energy harnessing center. I'm not going to spend time on this. The onus is on today is on developing new perovskite-based materials, both organic and inorganic, because the efficiencies in organic-based perovskite solar cells is estimated to be close to 30%. Then I'll talk about diamond now. The ultimate material, mechanical, electronic, chemical, you name it. This is very exciting for us in the last 1.5 decades. But before I go into the serious stuff, a little fun stuff, who doesn't like diamond, right? Kohinoor was a diamond that was mined in India 4,000 years back, and it had its value associated with it, but its structure was known only 100 years back after the invention of X-rays. Until then, we didn't know what is the crystal structure of diamond. But then it has this great value all these 4,000 years. Then in 1983, it was mounted on the magnificent theatre of Queen Victoria. How it went there, we know. And of course, there's another diamond called Hope Diamond you find in the Smithsonian Museum. And they acknowledge clearly that the origin is in India. In the other case, it doesn't happen. And there's one of the world's largest diamonds. It's always at the center of controversy, a diplomatic row between India and UK. With all these controversies around Kohinoor belongs to who, we decided to grow our own diamonds. Who cares? So we started growing nanocrystalline diamond using a CVD method, all the way from microcrystalline, nanocrystalline, and ultra nanocrystalline. And the applications are amazing. Of course, I'm not going to talk in detail about the mechanical applications. We have a big group of people from physics, my group on mechanical engineering, developing coatings for machine tools where the tool life is enhanced by almost 15 times based on the recipes that we develop. Thermal applications, diamond we know is an insulator, but it has a thermal conductivity 5 times more than that of copper. So that's the price he was talking about. So if you have the front portion of the missile or vehicle during re-entry that sees a temperature of 2,500 degrees centigrade, diamond can spread these hot spots within no time, right? And diamond being a hard material, it also stops the surface from getting ablated because of particle bombardment. And we are also working closely with medical people in Chennai. Recently, we have coated diamond. Diamond is also biocompatible. When we coated diamond on body implants and also dental implant, what has been found was there is no bacteria developing the dental implant, of course, which is made of titanium. Titanium itself is a biocompatible material, but you need an overcoat on that. So even after 2 months, there's no bacterial formation. The important thing with respect to today's theme is, what we are finding with respect to the morning talk on water purification. You can use diamond for water purification in a very big way. How is it done? You have, see, these are the advantages and disadvantages listed here. Now, one of the problems that was mentioned in the morning was arsenic contamination, which can be removed effectively by iron oxide. We also showed that iron oxide nanoparticles could be used to remove arsenic from contaminated water. But in India, the problem also is water contaminated with industrial waste. A lot of organic waste dumped into water. And what is done normally is, these water ponds you need to have several electrodes immersed inside the water ponds, and then you electrolyze it. And organic matter cannot survive when you pump in more oxygen into them, right? So these electrolytes basically produce OH radicals. And what has been found is, because the water environment is so harsh, the electrodes, which are very expensive, some farmers met us a couple of years back, neodymium, titanium, tungsten electrodes, they all start eroding. So now the latest solution is, you coat diamond, of course diamond is insulating, but I can make it conducting by doping. Boron doped diamond is coated on these electrodes, and with all these interesting properties, diamond is also corrosion resistant. Even if in harsh acid environment, it doesn't corrode. So that's what it is. Now, the present, there's a roadmap that we found last year, that ozonated water that you create very effective. So if I have a coated diamond electrode, then the number of hydroxyl ions that are produced is normally 3 or 4 times more than what the regular conventional electrodes can do. This is amazing. So it's all about using ozonized water with diamond electrodes for disinfecting, public toilets, hospital environment, even perishable food and surfaces. Fantastic application. And one application that's what we discussed with the people at Tesla was, of course, they use lithium batteries, a large number of them. The lithium batteries, one of the problems is at the other anode, you have the problem of dendritic formation. So one way to prevent that is coat graphite with diamond on top of it. And diamond prevents the dendritic formation, and also it helps in heat dissipation because of its high thermal conductivity. So lots of applications. And the last thing is, the story doesn't end there. There are plenty of applications. Now you dope diamond with nitrogen, and you create nitrogen vacancy defects. We don't want defects in crystals, but then defects can be used in a very good way, because if I have about 1,000 defects per 400 nanometer cube diamond crystals, but they have to be aligned in a specific manner. We are trying to work on it. We have a team working on utilizing nitrogen doped diamond for quantum computing. The future of qubits, of course, we know that qubits can be manufactured. It's been proved that we already have superconducting based qubits, but these qubits work only at millikelvin temperature. But if you're looking for a room temperature quantum computer in the future, it's going to be based on NV center based qubits. So that's why diamond is again going to be very useful. So thank you.
Thank you, next, I'd like to invite Dr. Robert Walker, who is the CEO and founder of Vigo. He has a PhD from Caltech and has been working for quite some time in silicon technologies and solid-state lighting, and both from the entrepreneurial perspective as well as the venture side of things. So, please.
Thank you very much. I did want to reference Dr. Kumar's talk. You mentioned about how China has become a big center of lithium-ion battery technology. India, not so much today. It reminded me I was back in Tianjin Institute of Power Sources, working with them on solar technologies back in 1999. I remember them presenting with great pride these boxes that they had outside their government factory, which were the first lithium-ion batteries ever produced in China in 1999. So I was in China when they were producing 0 lithium-ion batteries, 20 years later, they've become a powerhouse. Hopefully with you and IIT Madras, the same thing, same story can play out in India. But it does happen, but you reminded me of that story. I'll move back into radio and what I'm doing now. Radio's here, we're headquartered in Silicon Valley, we have an office in China. We've raised about 54 million in venture capital money. One thing I'll mention is a lot of the early money back 4, 5, 6 years ago when we first started the company came out of here in Silicon Valley. Applied Materials, thank you Applied, is one of our early investors. More recently, in the last 3, 4, 5 years, most of our funding is coming out of China. And so that relates to a little bit to the switch in focus that Murali was talking about in terms of funding for software and food delivery apps and things in Silicon Valley versus basic materials. We work in ultraviolet C LED technology, kind of a cousin to visible LED technology, but a different material system, so not indium gallium nitride that's used for visible and white LEDs, but aluminum gallium nitride for the deep UV. And we do all of our manufacturing here, the core manufacturing here in Silicon Valley of the LED components. So I'll actually pass this around. This shows you, and it's not so different from the LEDs in your cell phone, but these are the ultraviolet LEDs that we produce, and I'll just pass those around for people that want to see it. Very compact, look like an LED in your cell phone, but used for killing of bacteria, viruses, different pathogens in water, air, and surfaces. But we fully integrated from the core materials technology down to the applications, and we'll talk about that a little bit more. Whole bunch of applications here. This is a bit of an eye chart, but disinfection of water, air, and surfaces. There's also applications in food preservation, mold prevention, odor removal, phototherapy, vitamin D is generated in the skin under exposure to UV, treatment of diseases like psoriasis, different forensics, chemical analysis, things of that nature, as well as curing of inks and clear coat varnishes and things in manufacturing. So very much a platform technology which poses a challenge to the company in terms of the markets that we go after. There's markets like residential water, industrial water, surface care, health care, obviously hospital-acquired infections are a big problem, phototherapy, as I mentioned, industrial curing. So this posed certain challenges to the company, and give a little bit of the history and the way we've approached these challenges. We started out, and I think this is very relevant for the IIT Madras audience, we started out as a spin-out from Boston University. So we had about 10 years of core fundamental semiconductor materials technology research that happened at Boston University, funded primarily from the US government, partly out of the US Army, looking for solutions for water purification in the field for American soldiers. You can imagine if you're in Afghanistan, how much the US government spends shipping bottled water from Qatar up to Afghanistan every day for the soldiers to drink, or how many billions the US Army spent on water bottling plants in the green zone in Baghdad, just to give the American soldiers access to clean water. So having water in the field is a big deal to them. We took that technology, it was a one-off technology, one device, showed good promise, not manufacturable, no idea if it was manufacturable, raised the venture funding, spent the first 2 years just proving that the technology worked. And then the next 2 years, getting it into manufacturing. To the point now we can make literally millions of devices a year as compared to just one device. And then one thing that the company did that I'm very proud of is went downstream into modules so that it can be easily integrated. And then most recently we went and created our own consumer product, which is this large water bottle. So this is a water bottle, you fill it with water, you push the button on top, it's got a UV LED in the cap. In 60 seconds it disinfects the water, and then it turns on every 2 hours for 15 seconds to keep the bottle clean. And so for the US market, this retails for $95. You can buy it in Bloomingdale's, you can buy it in Neiman Marcus, you can buy it in the Museum of Modern Art, you can buy it online through our website. We've since spun it out as its own consumer products company. And for the US market, it's not about cleaning the water, because most water, you know, if you fill your water bottle here, you think the water is pretty clean. It's about keeping the bottle clean and keeping it from getting stinky, but it's also, for the American consumers, about getting rid of these things, and the plastics and the microplastics and the pollution. So this is very much geared towards a millennial crowd. Here you can get clean water on the go, and you don't have to pollute the oceans with plastic, but it's not too much of a leap to think that in places like China or India or Africa or Latin America, the same technology can be used to provide clean drinking water in off-grid villages where you just use solar power with a micro solar grid with a USB port. And that's kind of the vision of the company. And you guys mentioned you visited Tesla. We call this the Tesla model. When we released those UV LED components 3 years ago, we literally dropped the price of UVC LEDs on a $1 per milliwatt basis by 100x overnight. The LED that's in here, if you tried to buy it 3 years ago, would have cost you about $1,500. You couldn't make a water bottle. Now we sell it for $4. And with semiconductor technology, in a few years, it's going to be 50 cents. And if you think Elon Musk, if he had gone down to Detroit with his technology, which is electric drivetrain and a battery power management system, Detroit would say, we have internal combustion engines, what are we going to do with this? You wrap seats and a cup holders around it, call it a Model S or a Model 3, all of a sudden you've shown a future where you can have electric vehicles. And so this is meant to be a demonstration product for us of what the technology can do to inspire hundreds of different companies to adopt this technology, to provide clean air, safer hospitals, freedom from infectious diseases, where consumers are in control of their health and safety, rather than relying on government infrastructure, which, as we all know, in many parts of the world is sorely lacking. So that's an overview of the company. I made it for my 15-second cutoff, and I look forward to joining the panel today, and if anybody has any questions, please let me know. Thank you.
Thank you, Dr. So our final presentation is from Professor Pradeep.
Okay, good morning to all. So I'll dwell a little bit into the scientific part of where we stopped with Dr. Sujit and the others. So we had a good trip yesterday to their places, including applied materials. So I picked up two of these things, as you see here. One is on the anodes for lithium in batteries, and then concept of self-healing materials. So basically my group focuses more on these two aspects. This is called combinatorial alloy design, then atomic scale characterization towards understanding what materials we are making and how these atoms are basically sitting inside. So the first case of a battery, as he briefly said, I'll quickly go over. So if you use silicon as an anode material, it's the second most abundant material available, and it's non-toxic. But the major problem is that it undergoes a significant volume expansion of 300%, and that induces this capacity fade as a result of fatigue. So there are a few other requirements, but the main idea what we had was, if we now get the silicon in the form of a composite, where we have this little silicon nanoparticles embedded in a matrix of nickel, titanium, silicon. So this problem of volume expansion to an extent can be reduced, provided that the lithium goes into this nano silicon locations, whereas this matrix of nickel, titanium, silicon binds it together. So with that idea, so this was the concept we thought, and then the other moment there is a little bit research, not too much has been done by others, and we are also looking in the direction. So when we see that the lithium that's diffusing into the silicon, which is trying to expand this volume, is trying to an extent, if you have this a real material microstructure, you have all these little silicon infused into a matrix of nickel, titanium, silicon, and now if the lithium goes in, we are able to control the volume expansion not to 300%, but in a significantly lower level in an isolated silicon case. So there is some understanding that if you have a silicon particle of approximately 100 nanometer and the entire particle of a composite structure has a size of less than 45 microns, so this volume expansion to an extent can be solved. But the question is how efficient is this entire idea works and what is the lithium actually doing and where it is diffusing. All these kinds of fundamental questions are still not so clear. So now we can see here, this is what we thought. If you add silicon into this composite, it goes into these nanocrystals and then sits inside. And if you delithiate, we expect that all of this lithium come out. So that is the basic concept we want to try. But this picture gives an idea. So this is working together with a company who is producing these large amounts of lithium-ion batteries. So we gave this idea with the material in the final form, and then we got the material after this systematic lithiation and delithiation process. Now if you look at this image, so this is all the atomic traces of lithium that we have captured in a special microscope here. So all of these pink dots are all lithium atoms in the material. So at the end of this lithiation process, we observed that most of this lithium is somehow stuck at the interface, not too much into this pure silicon nanoprecipitate. And if you start delithiating it, you can see that even at the end of the delithiation process, there is still some lithium stuck at the interface. So this is the place where the lithium is lost. So the more and more lithium lost after frequent cycling, we end up having a dramatic loss of the entire process. So but this fundamental study of tracing the lithium atoms, where it's going and coming out, it helps us in understanding what we need to improve and what kind of things that can be optimized further. So in the second part of my talk, I introduced briefly this whole idea of combinatorial alloy design. So we worked on a material called the max phase. This is again in a very early stage of a research process. So where you have this early stage transition metal and combined with an A group element, and the X can be carbon or nitrogen. In a very specific proportion, it ends up into forming this special crystal structure where M and X are together. That means it behaves like a ceramic. And in between you have a nanolaminated A layer, which is fully metallic. So if you have this configuration, then what you end up is an unusual set of properties, something in the likes of diamond, what Professor Rao talked. So we have both metallic as well as ceramic characteristics. So this is a little bit strange. So out of this we have high electrical and thermal conductivity, thermal stability and stiffness. But what we were exploiting is the oxidation resistance. So I'll briefly tell you what is the idea behind this thing. So imagine that an aircraft is landing from an atmosphere at very high altitude, which is freezing at that point, and directly into a desert. And because of the thrust, there is a lot of sand particles that's hitting all of these propeller blades. So what happens is with time of the impact of these strong sand particles, it may be that there is a crack that's being initiated along the blades, and you can't replace these blades every 10,000 hours. It's quite expensive. So what we thought is that if you have this blade without any coating, maybe at the edge of it there is a sand particle hitting here, then you have a crack initiation, which may end up in catastrophic failure if it's not prevented. So we thought that if you have this kind of a max phase coating, because the air layer, which is the aluminum here, it can come out if you do some processing. So that means when you have this coating inside, if you notice there is a crack that's initiated, you just heat this material, the air will come out, so the aluminum atoms will come out. So aluminum has a natural tendency to oxidize in the atmosphere when it forms an alumina layer. So this alumina layer is far more harder, far more stronger than the sand particles here. So eventually that you will first of all fill the crack with this aluminum oxide that's forming, and that formed aluminum oxide is far more stronger than the sand. So this is the concept we tried. So now we don't know how much of these aluminum we need to add. So we made a combinatorial synthesis. That means we did the PVD process where we had two sets of targets, chromium aluminum carbide and chromium silicon carbide. Now if you look on the right hand side, this is the deposited region with a lot of substrates inside. So you get a systematic gradient composition going from the top to bottom. So the top is completely deprived of silicon, and when you come down, you have some alloying of silicon inside. So overall, we can estimate the collective properties of the same base material, but with varying content of silicon inside. So this is an example. So we annealed it with 1120 degrees, and you can see that with increasing silicon content, the oxide layer, the aluminum oxide which is forming on the surface, is increasing in thickness. That means we are able to fill the crack in case if it's forming until a length scale of micrometer within a fraction of the silicon addition. So with that concept, I just quickly go to the final part, that you add more and more silicon and you keep them as a function of time. So there is a natural process that's happening that the aluminum will come out, and this microstructure tells you along which direction the aluminum will go out. So this is all the nanocrystalline grains of the MagSpheres that we have developed. So ultimately, adding silicon, we can say that the scale thickness increases. That means you can, without any further coating, you can just have a self-healing behavior of a material that's inducing this crack healing process. So to summarize this part, for the whole group, so we did a lot of this combinatorial design. So we have one particular base metal, and we play with the composition space to identify those critical compositions and materials that have outstanding properties. Then we scale it up by going to the casting process, where you can see here, can do multiple levels of casting. If required, then we go to additive manufacturing, and we see again a gradient composition in the bulk scale. And we don't end up there. To understand the properties that we get out of all of these things, we induce this corollary microscopy, looking into the microstructure, precipitation, all that's happening in the metallic state, down to the atomic scale, where now we see the individual atoms that are forming clusters, or they are looking separated, and how these influences the properties. So this is a combination of both combinatorial alloy design as well as the atomic scale calculation that we do. So thank you for your attention.
Thank you, everybody. I'd like to invite my panelists up. We have a little time for questions. We've gone a little long, but we started a little late, so I'm hoping to beg your indulgence, if I may. If you have any questions for the audience, I'm not going to leave this mic right here. If you have any questions for the panel from the audience, please come up and feel free to ask. I'll start with a quick start to the questions. With again, we have a panel here that is partly academic and partly industry. So I was going to ask the panelists, how do you see the interplay between university and the actual startup, the innovation in the marketplace? We see so many technologies that we have heard, as you heard earlier this morning, maybe left the lab a little too soon and didn't actually make it into practical use, because when we actually put it in the field, it wasn't ready for practical use. And as we heard this morning, that's maybe more of a failure of the engineering than of the technology itself. So I just would ask for your response on that, and maybe each of your thoughts on that. I'll start with Dr. Kudu.
So to briefly start to answer your question, so the first thing, I see the interplay straight away, because when Dr. Sujit presented, he said the silicon oxide is kind of a material that seems to have an application purpose. But the question is, how did the silicon oxide being identified and where it came from? So there are lots of these things in periodic table. You can mix any metal with anyone else, but we still don't know much of them. So we maybe know of iron, carbon, basic metals, but there are so many other things which we don't know. So the academician's point of view, we look into multiple combinations and see what properties that we get out of them. But once we identify certain core area where we see these are the relevant metals, then I think that's the point where academicians transfer their knowledge to the industry people, where they can give a feedback of both cost efficiency, production feasibility, and the point where they can apply in a reasonable sense.
Great. Let me ask Dr. Kumar if you've got any thoughts about that.
I'm a big believer of public-private partnership. I'm also a big believer of startups and large corporations. They should partner with IITs and other eminent education institutions. One thing I want to point out, what happens in industry is you always look for ROI. If I put these $1 million, when will I get my return? For fundamental science, some of the ROIs you might get after 50 years. Does this mean that we don't do it? So that's where I see the role of IITs and national lab, that you have to keep us honest in industry, that this is exactly what's happening in your product, and you guys should be much more well-funded than what you are today, because you have to keep the ball moving forward to next generation. So as a company, we benefited a lot. We licensed our technology from Oregon National Lab a few years ago. Robert mentioned he licensed from Boston University. So these are the roles we think university is playing, kind of incubating a technology, bringing to a point of maturity where startups can come and license. And secondly, as startups are developing products, they will have some issues, so they should collaborate with universities and sort out those issues.
Great. So what I heard there was that startups will take technologies that are viable, but that the place of the university is to work on technologies that are not yet viable and maybe are 50 years away. But I don't think Diamond is 50 years away. Is it, Dr. Rao? I mean, why don't you argue against that?
Diamonds are forever.
The girl's best friend.
Yeah, so look, with all these 25 years of experience, in the Indian scenario, and let's start with the Indian scenario, things are changing in a big way. They're changing in two ways. One is that Indian industries are really interested in investing in R&D. I mean, they need to invest money and their time. We're going to spend time on the R&D part. And we also tell them that, look, I can find a solution for you. But then they need to give us enough time. And 10 years back, the story was different. The industry person would come and say, oh, I need this, can you do it in a month? No, technology doesn't come in a month. It doesn't fall from heaven also. But on the other hand, the other problem is, there are some industries, for example, there's a tool industry. We went and told them that, look, I will give you coded tools, you give them to your customers and get them their feedback. They didn't do anything. After 2 years, they came to us and said, now we are opening a research center in Chennai and we want you to be a part of it. I said, what has changed in 2 years? They say that, oh, when we go to the customers now and tell them this is our product, they're saying that, oh, similar thing we buy from China, and these guys are showing patents and research papers published on this topic. Do you have any? So because of that, they want to be with the...
Right. So they've only recently come to appreciate the academia,
Yeah.
is what you're saying.
But
Before they were very...
that is one class of industries, but then there are very serious industries that would like to be a part of research groups in IIT Madras, and they want to invest. And for example, the Murugappa group that we're working with in the last 10 plus years, they're very happy with what we're doing, and they also realize that this is a way to take their products to the next level. Yeah.
That's an excellent perspective. And so, Dr. Walker, what do you think? Is universities only good for papers? Or?
No, I think, first of all, I'll say the obvious that I think everybody knows. The idea of a public-private partnership between universities and industry works very well. Silicon Valley exists because of Stanford and Berkeley and these other things, and government funding, and the whole U.S. technology base is because of government funding and universities and national labs that have spun out in the industry. So there's no question that model works. I think what's more interesting are what are the challenges. And you mentioned I spent 6 years on the venture side, 20 years on the entrepreneur side. I've lived through this with my own company, Radio. I think there's really three fundamental issues. First, when you're in a university, you develop a technology, you spend 5 years, 10 years, whatever, developing this technology, and it tends to become a hammer, and you run around looking for a nail. And so you're like, okay, I developed this technology, Diamond or whatever. Where can it fit? And you really have to turn around that whole thing. What's the problem out there that somebody really feels that you can solve? Because if you're solving a problem that for somebody that's number 17 on the list of problems, they're never going to get to it. They're worried about problems 1, 2, 3. And if you're solving a good problem, but it's number 17 on somebody's list in industry, it's never going to get adopted. So you really have to turn around. And that happened with our own company. My co-founder wanted to go after municipal water disinfection because that's where UV is used the most. It would never work. We had to go after consumer applications where mercury bulbs aren't a good solution. Second piece of advice is you really have to make sure this technology can work on a commercial scale. Universities are very good at one-off, kind of proving it in principle. Batteries, I look at a lot of battery technologies. Correct me if I'm wrong. One of the challenges of batteries, in my opinion, is you got to get about 20 things right to make a commercial product. If you get 19 of them right, you're nowhere. It's got to be reliability, it's got to be safety, it's got to be energy density, it's got to be power density, it's got to be all these different things. And so in a university, you'll maybe improve 2 or 3 of those aspects. But if you all of a sudden fail in 1 or 2 others, as a result, as a byproduct, you can't make it into a commercial device. And that's a real challenge. So you have to think about those things.
So we have one question, a couple of questions from the audience, and I want to give an opportunity to ask them. Go ahead.
I'm kind of tickled because, the kind of research that, just amount of, the kind of presentations you people presented is simply out of the world. So, let me come to the main issue that I actually wanted to bring. When you mentioned that it costs about $7,500 and it goes for only about 600 times you can charge, this is a question for Kumar. I wanted to understand where exactly it is with respect to competition in terms of what is going on in lithium ion, your competitive, this thing. $7,500, 600 charges is about 1.5 years of probably lifetime for the particular battery pack. So I want to understand from you, is that a norm in the industry? Is that something you need to replace more often? Can it be linked in terms of longevity?
So let me address 2 questions. One you asked about the cycle life. So today the requirement is 1,000 cycles. So our silicon anodes have cycled 1,000 times. And if you think of it like, let's say, a Chevy Bolt, which has a range of 200 miles. So 1,000 deep discharge cycles means 200,000 miles. So now, something like GM, they can warranty their battery for 200,000 miles. I did not talk about the calendar life. You also need to meet at least 10 years of calendar life. So that's a requirement. And in terms of cost, today's battery cost, there are at least $200 per kilowatt hour for a battery pack. So if you have a 50 kilowatt hour system like Chevy Bolt, it will cost $10,000. And we are not making profitable cars, so you need to bring the cost to at least $7,500.
Hi, I'm Rishi. I'm the president of IIT Startups, and we have a lot of startups, over 200 startups from the IIT circuit. About the university to startup collaboration, on 7th of November, we're going to have a joint meeting of SRI, that's Stanford Research Institute, and us. They are going to expose us to all the technologies that they've built, which our startups are too impatient to go into the long run cycle, but if something is very close to launch, they might pick it up and run with it. So basically, the long run part has to be left to the universities and organizations like SRI to do, and we are trying to take all our startups to those guys and have a look. But again, within that, I see the startups have a very strong bias towards software, because that's very quick. Anything to do with hardware is long run and highly capital intensive, which they kind of are hesitant to get into. And in Madras also, there is an organization called GDC, Gopalakrishnan Deshpande Center for this thing, and they are doing the same thing. They're taking the IIT Madras, research outputs, and they're trying to commercialize that. They're trying to see how to take it to market. So that's broadly the thing. 7th November, guys. We have an event at SRI. I'll let you know about that.
We'll take a last question here.
Yeah, go ahead.
I actually had 2 questions, or 2 of them, if that's fine. The first question was for Dr. Pradeep regarding your research of self-healing materials. So I guess those research have been going on for more than 10 years now, and there have been multiple applications from road repairs to glass repairs and some acrylic materials as well. So how controlled are the self-healing processes right now, since the process has been going on for so long, and the example you gave is very close to aerodynamics, so you can't just have uncontrolled expansions there. So how does because I'm pretty sure that your research is not at full-fledged process right now, you're just experimenting things. That's the question for you. Like, how long do you think it would take for you to get into a state where you can control the process?
Okay, so to partly answer this, the first thing on that part what I showed is that we are working with Brad earlier.
Right.
So the clearance distance between this propeller and the enclosure is hardly 3 micron.
Right.
So anything that I do here, the
Right.
coating has to be 1 micron.
Right.
Anything that forms on the crack or the clearance angle, it should be hardly 500 nanometer.
Right.
So at that length scale, with this idea, it is close enough. But if it grows something more than this,
Right.
then it's a problem because it's stuck everywhere. It's going to scratch the entire surface.
It is.
But on the contrary, what I showed is that you heat it at 1000 degrees for half an hour to get this right.
Right.
But that they cannot do. I mean, you start heating this blade at 1000 degrees,
It
it will melt half of them.
on its own.
So, but the idea is, if you can grow these things without destroying the coating that you have,
Right.
on the other hand, reduce the temperature, increase the speed of healing the crack, then it works. So now we have to explore which element that you add to the coating that will enhance your kinetics. So it will increase the rate of healing within a shorter time, lower temperature. Then I think it's okay.
Thank you. And the other question I had was for Kumar in relation to the question he answered earlier about the number of cycles that the battery can recharge. So just last month, Elon Musk, he declared that there has been a research by Jeff Den from a university that they have found a way to increase the number of cycles to 4,000 times instead of just 1,000, which is the industry standard right now. And that is also set by Tesla, actually. So how far, because you just said that you are still trying to get to the 1,000 cycles mark, and they are just trying to cross 4 times that. So how far do you think you are to that? Because their battery prices, what they estimate is roughly about $40,000 compared to $7,500 that you have right now. With the market growing, I'm pretty sure that the rates are going to come down for both of you. But how far do you think you are from reaching that? Because they're going to be using pretty much the same materials that is being traditionally used with lithium and the cathode. So basically, how far do you think you are to reach that level? Because that's what the industry standard is going to be in the next 5 to 10 years.
So one thing, electric vehicles are, entering a very interesting space. Right now, somehow all the news has been like, the minute somebody comes up with a new electric car, they call it Tesla killer.
Right.
It's not like that. Every automaker, if you read the announcement, GM will have 10 different models, Volkswagen will have 25 different models, Tesla will have many different models, and you will have many kinds of batteries. So some battery will focus on, like you said, within the wallpaper of sedan, it will focus on very, very long cycle life. Why is that important? Because most likely, a few years from now, you will have a self-driving car. While you are at work, your car is also at work, making money for you. So in that case, it needs very long cycle. Some consumer will prefer, I don't care about 300 miles car, I just want a 100-mile car, but I want it to be charged in 5 minutes. So that I can get to work and can come back from work. So that's the kind of technology we are focused on a very fast charge that you can charge in 5 to 10 minutes, but it also lasts 1,000 cycles. So my point is that there are many different kinds of batteries, many different kinds of model in 5 years from now, and and you have to solve many different problems.
I think that's answered my question.
Thank you. So we're out of time. There is time for lunch. So thank you. I hope this was useful for everybody and educational and entertaining. Please give me a second.
Whoever has my little LED packet, if I could get it back, I would appreciate it. Thank you.
I have a couple of announcements to make.